This video will explain how to design a lens in just a few minutes using Lenskit.app. This is the landing page, and first I'm going to switch to daylight mode for the video. I'm going to log in. If you don't have an account, all you have to do is put in your email and create a password, and you can create an account. There's no charge. Go to login. The home page on login contains all the previous designs you've worked on, if you've worked on any. So these are lenses that I've already designed, but today we're going to go into the lens designer, and we're going to design a new lens. It'll be a zinc selenide lens for 10.6 micron. I'll leave it at 25.4 millimeter. And we'll use a best form lens, but we're going to make the focal length 127 millimeters and create a lens. And here's our lens creation. You can see on the top of the screen here is a ray trace. You can rotate this around. You can also expand it to full screen and look at the ray trace in different views. You can turn the beam off and show axes in case you want to know what coordinate system the lens is used in. To the right is the lens source. So right now the lens is being evaluated using a collimated flat top 10.6 22. We're going to switch this to a Gaussian beam of 20 millimeter diameter, outer diameter, but the Gaussian diameter we're going to use to be 10 millimeters. So we can switch to the lens parameters, and here are the lens parameters. The top of this panel shows the material diameter, CT, ET. A little bit down below on a side panel shows side 1 parameters, aperture, radius. If it was an A-sphere, there would be aspheric terms here. And we can switch to side 2, and we get the side 2 data. Radius, same information as side 1, radius and aspheric coefficients, if there are. Now, when you have a light source of collimated Gaussian beam, the data that is shown is the wavefront data here on the top left panel, middle left panel. Here is the point spread function, which in Gaussian mode is equivalent to the Gaussian beam diameter at focus. So it's showing us that the focus diameter is simulated by this program as 176 micron. These two have a 3D profile if you want to go into 3D mode and see the wavefront error. It's pretty small. Same with the point spread function. It reaches 1. Scroll on down, and the bottom two panels show spherical aberration and spot diagram. Now, when you expand the spot diagram graphic, it shows the through focus spot diagram. So here, going in negative millimeters is back towards the lens. Going in positive Z is going away from the lens. And you can see if this is our image plane, and you can see the spots are a little bit larger. Actually, they're smaller at the minus 25 millimeter point. So, and you can zoom in, and you can see that at image plane and this point they're smaller. So that's indicating some spherical aberration. And actually, if we look at this, if we look at the spots here, like the beginning spot, the distortion of the spots indicates spherical aberration. If there was no spherical aberration, these spots would be in a nice evenly spaced grid pattern, vertically and horizontally. But that's not the case, so there's some residual spherical aberration in the lens. And finally, we can save the lens to our database of lenses, and we'll call this zinc selenide example 1. We can now go a little further And because we have some residual spherical aberration, that you can actually see if you zoom in on the focus of the lens. You can see that the beam is going through a small focus or smaller cluster of spots just ahead of the image plane. Again, that's an indication of spherical aberration. So one way we can modify that is to aspherize it. And ideally, you want to aspherize the lens with as few as terms as possible. We could turn all these on and click Asphere, Optimize, and now it'll click it a couple times to get the best result. And now we have a wavefront distortion that's very small and 25 millionths of a wave. And if we look at the through focus now, you can see that the minimum spot is at the image plane. And if we zoom in on one of the spots ahead of the image plane, you can see the even distribution. So again, this is an indication that in this case, the lens has very little spherical aberration. This lens was pretty good performing anyway, so you won't see much difference in the focus spot size, though, shown by the Gaussian point spread function. And we can save these changes to our zinc selenide example. And that's how you design a lens fairly quickly in Lenskit. Thank you.